Okay, so now it's time to create random walks, which are going to allow us to trace the path of a stock price through the binomial tree in kind of an abstract sense. So we are going to look at every movement upwards as a +1 and every movement downwards as a -1. Now what we need to do here is every movement up can be seen as a success, movement down can be seen as a failure. What you can do mathematical software is going to have a similar recipe built in. And the recipe that we have in Mathematica is going to be called upon when you call the random integer. And the random integer is going to give you a randomly chosen integer between 0 and whatever is in the argument of your command. So this time around it's going to be either 0 or 1 because those are the only ones up to 1. So you get a 0, or you get a 1, or you get a 0 and it looks boring, or you get a 1, and then it seems like they're alternating, and they're not completely alternating, as you can see, so it is random. My next task is going to be to create a random walk of length 10. So all I want to do is to have 10 random steps. What I'm going to do next is I'm going to stipulate that the length of the random walk is 10, and then for short I can call it n. And then what I'm going to do is create a list of Bernoulli trials, which is going to be what I get when I call the random integer command for zeros or ones, and when I have n simulated values, in this case just 10 of those. And L stands for list, and Bern stands for Bernoulli. So let's see what we get. We get 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, which is nice and looks random. So to create coin tosses out of these Bernoulli trials, I need to modify ones into ones, which is not a modification really, but then I also need to translate zeros into negative ones. And a simple linear transformation which does the trick is this one. So just think about it. If you have a 1, 2 times the 1 is 2, minus the 1 creates a 1. If you have a 0 as the input, then 2 times the 0 is a 0, minus the 1 is a -1. So this simple manipulation creates coin tosses out of Bernoulli trials. And you can actually visually just check that all of the ones are mapped into ones and zeros are mapped into -1s. What the random walk does is that it accumulates all of the steps that have been taken from the beginning of time up until a certain moment. And luckily, there is a command in Mathematica which does exactly that. There is a command which is called accumulate, which takes all of your entries from the beginning of the list and sums them up cumulatively up until the index in the list. So L walk is going to be the list corresponding to the walk that I get through accumulation of coin tosses. Look, -1, -1, -1, -1, that's -2, +1, that's -1, +1, that's a 0, minus the 1, that's a -1, etc. until the very end. So it does work out. What I would like to do is I would like to have a picture of my random walk. And then if I try to do it using a simple command called list plot, I am going to get exactly what I asked it to plot. So I'm going to get a -1 at the first spot. I'm going to get a -2 at the second spot, etc., etc. What I do not have is that all of these dots, which are really the values of my random walk, are connected, which is the way that we usually draw them in the binomial tree. Now I can just blindly try stuff, but it's not going to give you what you want. If I join them, then it works out. It's just that the 0th one is not joined because it's, formally speaking, not in the list. So what you want to do is you want to prepend 0 to your random walk. Unfortunately, the effect that that little manipulation has is that 0 is now your first in the list, and mathematica counts from 1. So what we need to do is we need to create a table, and that table is going to transform your walk into a plottable walk. And what we do is we just simply create a table of pairs, which give you the index minus the 1, accompanied by what is in the walk itself. So this is a nice little function, which is always going to take your sequence of positions in the list, and then it's going to just shift everything index-wise to the left by 1. So in our case, when we use our new function walk to plot on our list, what do we get? We get that we start from 0 for the index 0, and then every single one of the following indices for the time is going to be accompanied by the position of your random walk. Now let's see if it works when you try to draw it. And of course it works. So this would be just one random walk that you've got. Our next step is going to be to see, one, how we can take the limit, or pretend to take the limit rather, because we cannot really take the limit in a computer, by taking denser and denser random walks, meaning that they have more and more steps, with each step actually being smaller and smaller, really. And luckily, the computer does the scaling of the picture for us. And then we're going to see how we can use it and what use there is of this kind of an approach to modeling of our stock prices. Thank you.